Okay, today we're going to be talking about chemical reactions that are able to reverse themselves. And so let's take a look at this. So here we have our typical chemical reaction, and this is the production of ammonia here. And we have our N2 gas reacting with 3 molecules of our H2 gas, and we're producing 2 molecules of NH3 gas, which is ammonia. In this reaction, of course, just as a reminder, we would call everything to the left side of the arrow's right here, the reactants, and everything to the right side of the arrow would be called the products. So as this reaction is written, we say that the reactants are reacting to form products. This reaction, we say, is shifting in the forward direction, or we're saying it's shifting right, meaning as the N2 and the H2 are reacting, we would say that the concentration of these guys is decreasing as this reaction is moving along. We have less and less, and as it shifts to the right, the concentration of the ammonia, the NH3, is increasing. So that's just kind of a review. Now, we can also talk about reversible chemical reactions, and that's our definition here, a reversible chemical reaction. And this is a reaction that can occur simultaneously in both directions. So they're often denoted by a double arrow, and that's what we have here, a double arrow. And sometimes you'll see this arrow written this way, and sometimes you'll see it just written as an arrow pointing forward and an arrow pointing backwards, just like that. And what this means is, as this chemical reaction occurs, we have forward reactions occurring, and we have reverse reactions occurring simultaneously. They're both occurring. Now, not all chemical reactions are able to do this. Some of them are, though. So once again, the forward reaction is going from the left to the right, what we would typically think of in a chemical reaction, and the reverse reaction is going from the right to the left, or we sometimes would call it going backwards. Now, when these two things occur, when these two reactions occur, the forward reaction and the reverse reaction, at the same rate, meaning how fast they're occurring, we say that we have what's called chemical equilibrium. Real important part of this is we have the forward and we have the reverse reactions, and it doesn't mean that they have the same amounts. It just means that they're occurring at the same rate. And we looked at rate the other day, and rate is typically listed as moles per time. So preceding maybe moles per second or minute in a relatively fast reaction, or maybe moles per hour or days or years for a slower reaction. So it's rate. It doesn't mean that there's the same amount. I'll say that again because it's really important. Now here's a little graph that kind of illustrates what's going on here. And so let's kind of analyze this graph here a bit. And so here is our reactants line. And so the reactants, starting off this reaction in the forward reaction, we start off about 0.4 moles per liter. And so the reaction starts, and as this reaction starts, you can see the concentration of the reactants is dropping. And it continues to drop until it gets to a point where it kind of levels off. Right about there is where I'd say it's leveling off. Now, as this reaction starts, you should also be able to notice that we start with no product at all. This is our product line. And as this reaction occurs, our product starts increasing, which is kind of what we expect from a chemical reaction. And we also see that this product kind of also flattens out right about here. So now, typically when you get this flat line, this is where we say we have equilibrium. That flat line doesn't mean the chemical reaction stopped. It just means that the forward and the reverse reactions are now occurring at the same exact rate. How fast the product is being created is the same rate as the reactant being created in the opposite direction. Now, there was a French chemist that studied these reactions at equilibrium and came up with the idea of Le Chatelier's principle, named after Le Chatelier. And what Le Chatelier's principle says is this: if stress is applied to a reaction at equilibrium, the reaction will shift to reduce the stress. So the first stress that we're going to talk about today is the stress of changing concentration. This is either increasing the amount of reactant or product, although, and I should say, we can also decrease the amount of reactant or product. That's the first of 3 stresses that we're going to be talking about. So let's give you an example of what we're talking about here in this reaction. Okay, so this chemical reaction here we have 2 SO2 gas, sulfur dioxide, reacting with O2 gas to produce 2 SO3, which is sulfur trioxide, in the forward direction. Also in the reverse direction, what we have occurring is SO3 gas decomposing in the reverse direction into O2 plus SO2 gas. So let's talk about some of the things that we can do here. One of the things we can do here is we could increase the amount of SO2 gas that's in the container that's holding this reaction. Maybe we attach a gas tank to this container, we turn it on, and we pump SO2 gas in. Okay. We could also, and so that's one way we could affect this reaction. We could also increase the concentration of the O2 gas by pumping in O2 gas, or we could pump in some SO3 gas, and these would all be stresses, or we could remove any of the 3 gases, and that would be a stress to the equilibrium as well. So let's say in this container we have come to equilibrium, and then we're going to apply our stress. So let's say the first stress that we're going to apply is we are going to remove some of the SO3 gas. We're going to remove it. Now the trick with removing one of the reactants is the chemical reaction will shift towards whatever you remove. So we would say that if we remove SO3 gas, this reaction is going to shift in the right direction. When you shift in the right direction, it's going to be going towards whatever's being removed. Okay? So let's give you another example. Let's erase this. Let's say we remove some of the SO2 gas. Hopefully now you can predict, here's our kind of dividing line between reactants and products, you can predict that the reaction is now going to shift towards whatever you remove. So we would say that this reaction would shift to the left. Okay? Let's give you another example. Let's say that we're going to, in this case, we're going to add additional oxygen to this reaction. Now, adding something is the opposite of removing. So whenever you add something, it shifts away from that reactant or product. And once again, our dividing line is our double arrow for equilibrium. So this is going to shift right, and that'd be what would happen there. Okay, let's give you one last example before we do a couple practice problems here. And let's say that we are going to pump into this equilibrium. We're going to add some SO3 gas. Okay, we're going to add that. Again, our dividing line is our double arrow. And so when we add SO3 gas, hopefully we can now predict that this reaction is going to shift away to the left. Okay, so let's scroll down here and take a look at this same exact reaction, and I'll have you predict what's going on here. Okay, so if you would like to pause the video right now, what you could do is you could pause the video and try this yourself and then press play and see if you get it right. So we have the same exact reaction. In the first example, it says predict which way the reaction will shift as oxygen gas is added. Okay, and the second example, predict which way the reaction will shift as SO3 is removed. So you can go ahead and pause the video now if you want to try this at home or at school, and come back here in a minute. Okay, here we go. So we're going to predict which way the reaction is going to shift is if oxygen gas is added. So we're adding oxygen gas in our first example. Our dividing line is our double arrow. And so if you're adding something on the left side, this will shift to the opposite direction. So our shift is towards the right. And hopefully you predicted that as well. Okay. And let's erase this off here, and we'll look at our second example. It says predict which way the reaction will shift if SO3 is removed. So we're removing SO3. Dividing line is our double arrow again. So remember, anytime you remove something, it shifts towards it. So it's also going to shift to the right in this case. Hopefully you got both of those right. Now the last thing we're going to talk about with respect to Le Chatelier's principle and changing concentrations is we can predict what's going to happen to concentrations based on which way the reaction is going to shift. And so it says predict what happens to the concentration of oxygen and the concentration of SO3 if SO2 gas is added to a reaction vessel that contains this reaction. Okay, so we're going to start out predicting which way this reaction is going to shift. So it says right here, SO2 is added. So we're adding SO2. There's our dividing line. And from our previous example, we decided that if you add something on the left-hand side, it's going to shift to the right. So we know, first off, it's going to shift right. But that doesn't tell us what the concentrations of these reactants and products are doing. So here's how we analyze this. If the reaction shifts to the right, that means we will increase the concentration of SO3. The reaction is going right, the concentration is increasing. And whatever you're shifting away from will decrease. So we would say that O2 is decreasing in this chemical reaction. So what we would say is the correct answer, and we like to use brackets to denote changes in concentration or concentration themselves. We would say that O2, again, that bracket means concentration in chemistry, the O2 is decreasing, and we would say that the SO3, again, bracket means concentration, is increasing. Again, whatever direction you're shifting towards, will increase. Whatever direction you're shifting away will decrease. And this is Le Chatelier's principle. This is the first of three stresses that we're going to talk about with respect to Le Chatelier's principle. We can add or remove as a review. If we add something, it will shift away from it. If we remove something, it will shift towards it. And then we can use that shift to predict what occurs to the amount of concentration and a reaction at equilibrium.